Good morning, everyone. Thank you so much for joining us today. My name is Victoria, and I'm a Senior Business Development Coordinator at 2H Offshore. We started this webinar series last year in April during COVID lockdown and held a live webinar every 2 weeks in 2020. Going forward, we'll be hosting the events monthly, so we hope you will continue to join us and find the information useful. Today, our webinar is entitled Risk-Based Decisions for Corrosion Management of Subsea Systems. Before we get started, I'd like to cover a few important housekeeping items. Firstly, this webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, please feel free to contact our speaker directly after the presentation. So with that, I'm very happy to introduce our speaker today, Johanna Rurako. Johanna is a principal engineer at 2H's sister company, Claris, and has over 7 years of experience in integrity management of offshore facilities, risers, and subsea equipment. She's based in Claris's Houston office, where she leads multiple engineering projects and supports several operators with development and execution of IM programs, as well as life extension evaluations. Johanna holds a Bachelor of Science degree in Civil Engineering from the University of Houston. So with that, I'm going to pass things over to Johanna to get us started today.
Thank you so much, Victoria, for the introduction. I'm very happy and excited to be sharing this topic with everyone joining us today. The objective of this presentation is to show you how we use the risk assessment process to improve visibility of risk, prioritize IM activities for internal corrosion management, and support asset life extension. With that, we're going to review key challenges that we see across our different projects, review the risk assessment process, IM plan recommendations that are typically used for internal corrosion management, and go over what type of things trigger additional assessment. Review a couple of case studies in which these elements come to play, and then go over final conclusions. So what key challenges we see across many of our different projects is that corrosion risks change over time. That can be from changes in operating condition, produced fluid properties, additional wells tied back to a field that will impact and change the profile of the corrosion risk. The other challenge that we see is that most common data retrieval methods that are used provide indirect data on the condition of the subsea system, offering limited time for remedial measures. An indirect method might be corrosion coupons at the facility that are not directly in the flow path of that we're interested of, but does provide trending data, versus a direct method such as inline inspection or non-destructive examination that might offer direct measurement of the internal corrosion hotspots that we're concerned of. And finally, the balance between the time, cost, and effort of implementing IM activities versus adequately identifying and managing those risks, creating that link between data and degradation mechanism that will support our management strategy. So the risk assessment process is the tool that we use to adequately identify, quantify the risk, and identify what mitigation, monitoring, and inspection activities are going to help us manage that risk throughout the life of the asset. And the key thing is that we are always feeding back information to this process. That way we can adjust and implement in with sufficient time prior to the onset of the degradation mechanism. So once we identify a system scope and divide it in unique sections that can be assessed, The typical risk events that we evaluate are localized and general degradation of the pipe ID. We also might look at deep localized pitting corrosion that can result in a leak. Key parameters that help us determine the threats and applicable failure modes. We look at the corrosive species, sweet service, CO2 corrosion versus sour service, or is oxygen present in the system. We look at the electrolyte. What are the brine properties? Are organic acids present? We look at the flow regime. What are the water, oil, wet conditions? Are those well understood? Or do we have data just from design? Or sometimes we don't have sufficient data on those parameters. Finally, flow rates, pressure, and temperature. Are flow rates increasing the likelihood of the corrosion mechanism? Is it disrupting mitigation strategies such as corrosion inhibitor, or is even unsetting corrosion? In the system review, what is the material selection across the entire flow path? Design allowances or no design allowances if not available. What are the applicable degradation models that were considered in design and then updated throughout the life? And if they're up to date with the most recent operating conditions. Was the chemical, if corrosion inhibitor is implemented, qualified against those conditions, and then has it been updated throughout the life? And that helps us determine the risk, and any inspection data, monitoring data that feeds back into the confidence assessment that helps us space out or warrant more frequent inspections and monitoring activities. And that is documented in the IAM plan. But if there's too many data gaps, we have not a good understanding of the degradation mechanism or the parameters that are key, as we mentioned, that might lead to a lower confidence level and more conservative risk assessment, which will warrant more frequent monitoring, more frequent inspections. So as we go through the life of the asset, it's key that all the assumptions are documented. And we use this process to do that, to create a cohesive history and to improve and maintain confidence over time. So we're not warranting annual inspection, and we can document those trends accordingly. So what does an IAM plan recommendation look like for internal corrosion? Some of these activities are already part of your plan. Some of them might be things that you're considering down the line. So monitoring at the facility, we typically have corrosion rate monitoring via corrosion coupons or probes, fluid sampling and analysis of the fluid. Sometimes it's commingled fluids, might not be entirely representative of the subsea field, but it can help you trend the overall corrosivity of the fluid. Inspection tools. Are we considering external NDE tools to screen for general or localized corrosion? And then finally, inline inspection, ILI, which provides the most coverage for the subsea system, as well as the highest data resolution. And finally, monitoring subsea. We're looking at the flow rates for individual and commingled wells, the pressure and temperature at key points, not only at your well, but also at your flow line inlet and your arrival at the facility. What are your injection rates and the availability of that corrosion inhibitor? Are we meeting our target dosages over time? And all of these recommendations form your IAM plan moving forward and might be updated on an annual basis as required based on the risk level. What triggers additional assessment? This is the key question as we are looking throughout the life of the asset, the risk level, how does that change, and when to reassess our management strategy. Typically, at the beginning of life, the risk is higher because we need to confirm that our mitigations are in place. We need to confirm fabrication records and that our allowances were implemented are well quality, that we can deliver the corrosion inhibitor rate and meet our targets. Once those barriers and mitigations are confirmed, then the risk becomes at an acceptable level. But then as time goes on, water production we might start lagging on the injection rate adjustment for CI, and that warrants a reassessment of our strategy. Should we be monitoring more frequently the corrosion inhibitor rates in order to ensure that we're meeting our target? And once we do, and that's any changes are required and implemented via our IM plan, the risk becomes at an acceptable level again. But again, if things change with the water chemistry or the produce gas chemistry, it again warrants another reassessment. We might requalify the chemical for the current operating conditions and fluid properties, bring that risk level again to an acceptable limit. And then as we reach the end of life, where we are expecting to have meet our corrosion allowances, and especially if we're looking to continue to operate an asset beyond its original intended service life, the risk start to increase again, and we might want to look at direct measurement inspections, especially if there's not a history of inspection activities and direct measurements. That's when we start thinking about those things to prioritize those activities, and again put that plan forward for either the remaining of the service life or of that life extension plan. So now we're gonna go over a couple of case studies. Our first case study is a well jumper. It's a rigid well jumper. The jumper had been in service for 2 years. We had conducted the baseline risk assessment. Our driving internal corrosion mechanism is sweet service CO2 corrosion. Design assessments indicated that there was a low potential for water wet conditions. In fact, we had very to no water production at that time. The risk event through wall localized corrosion of the jumper had a high consequence of failure, but with the active risk management via corrosion inhibitor, we had sufficient data available that had a very low probability. Our management plan included corrosion inhibitor injection and monitoring availability, that uptime of how much of our normal operations we were meeting the target dosage, and monitoring the corrosion coupon rates at the facility. Again, not a direct measurement on our jumper, but indicative of the corrosivity of the fluid and what our jumper might be seeing. However, as you see in the graph that is to your right, on year 3, we started to rapidly see water production increase. And by year 4, we were at 40% water cut. So with that, the water cut was increasing at 2 to 5% every single month. And similarly, at the same time we were reaching 40-50% water cut, we saw that our corrosion coupons were exceeding the acceptable KPI limit for corrosion of 3 mils per year, which is determined by our corrosion allowances as well as the design of that asset. We also observed pitting in some of the coupons. Therefore, that elevated that risk level and made us had a lower sense of confidence in the effectiveness of the barrier that had been implemented, which was CI injection. With that, we wanted to look at how the water cut was affecting the corrosion rate and determining the water wetting characteristics in their impact. Again, from design, we had that there was a low probability of water wetting, but now as we were cutting water more rapidly, that those design assumptions are no longer valid, so we wanted to reassess. What we found is that at water cuts of greater than 50%, between 50 and 90%, the corrosion rate was greatly impacted. It increased rapidly, as you can see on the bottom graph. And so the next step was, let's look at the chemical at another potential chemical, and can we meet our acceptable corrosion rate of 3 mils per year at the different water cuts. So we looked at, we conducted rotating cylinder autoclave testing with the lab, performed at varying water cuts. So since we were at 50% water cut at that time, we looked at 50, 70, 90%, both uninhibited samples and inhibited samples. We found that both chemicals had acceptable corrosion rates under those conditions. But the next thing was to look at availability. If we are meeting our target dosage 90% of the time versus 95% of the time, are we within those acceptable KPI limit for corrosion? What we found is 90% availability at the higher water cuts, we were above our acceptable corrosion rate limit. At 95%, we were for all the water cuts, we were below 3 mils per year. And so we set that as our target availability that we had to maintain. And with that, moving forward, once we increased the dosage, we started seeing a decrease in the rate of the corrosion coupons that were retrieved over time, even though that water cut continued to rapidly increase. Therefore, there was a good reliability between the data that we were retrieving and our models in place. The update to the dosage and the KPIs for CI availability was managed through the IM plan, and we additionally increased the monitoring frequency for CI availability to be able to ensure that we were consistently meeting our targets, maintain that same level of confidence, and defer further assessments to later the life of that jumper. In our second case study, we're looking at a pipe-in-pipe flow line. This particular case study, as you can see on the graph on the right, we had an oil pipe-in-pipe flow line in this field that conveyed production from 2 wells back to a facility in the Gulf of Mexico. The other pipeline in the field was a gas flow line that was not being used for production and was in suspended service. So there's no redundancy in the production flow path. So it's key that the integrity of this one pipeline system is confirmed. The other key items, as we did risk assessment a little bit later, midlife of this field, and we started implementing the IM program, there was no corrosion inhibitor injection due to several umbilical blockages that were limiting the capacity of the umbilical. The risk event, again, through wall corrosion, with a very high consequence of failure, not only because it's a pipeline, but also is the only pipeline for that tieback. And with a medium probability, because of a passive risk management strategy, we were monitoring rates of the corrosion coupons, we were monitoring produced fluid, but not actively mitigating with CI and not conducting inspections. Another key thing is operational pigging had not ever been conducted for this flow line. So when looking at what activities we could do at that time, pigging was not considered feasible. We did look at bespoke solutions, but our goal was to assess the risk in alternative solutions to pigging. The IM plan included corrosion rate coupon monitoring, as I mentioned before. We were also doing periodic fluid analysis, and in addition, we recommended a corrosion model update because the field had been in service at that time for a couple of years when baseline risk assessment was conducted, and so corrosion model update was warranted to confirm what the corrosion rates expected given the uninhibited conditions. Furthermore, during annual integrity reviews, we start to observe exceedance of elevated KPI limits for corrosion rates. So we were sometimes exceeding the elevated KPI limit, sometimes exceeding the critical KPI limit of 4 mils per year. We also observed the presence of organic acids in the produced water, which was not a design assumption. It wasn't identified during this design stage. So that was a change in production chemistry that led to an enhanced corrosion mechanism. When for uninhibited CO2 corrosion, we expected the pipe ID will form a iron carbonate film that will mitigate corrosion rate over time. So it was not very a high corrosion rate throughout the entire life. However, with the presence of those acids that disrupt and destroy that film, we will expect that the corrosion rates continue to be at a high levels throughout the life of the asset. In addition, what we observe during annual reviews is at some point the corrosion coupon location that we had at the facility was moved, and it became non-representative of the subsea field. The non-representative data is shown in the graph in pink, and as you see, it significantly dropped the corrosion rate, but it was no longer representing the field conditions. Through the annual review, this was identified and addressed. But again, we had a limited understanding of the risk level, and we wanted to have more clarity in defining an IM plan for the remaining service life and the potential life extension of this asset. So the key challenge was to link the available integrity data that we have for over 10 years of operations to the degradation mechanism. And with that, we chose 3 low cases to look at: early life, mid-life, and late life. In early life, we only had operating conditions, pressure, temperatures, flow rates available, and the corrosion rate KPIs. We had to assume water chemistry and CO2 content per design conditions, since there was no water chemistry done in those early years of production. There was no presence of organic acid based on the design assumptions, and we assumed the corrosion rate was negligible because the water cut was significantly low. We did conducted flow regime analysis for benchmarking on that early life case. Then when we looked at the midlife, we had the corrosion model available from the implementation of the IM program. We had water chemistry, operating conditions, and corrosion rate KPI. So we only had to fill in the gap of the flow regime to assess what the water wet areas at that moment in time were. And towards the late life, we had operating conditions, corrosion rate. We conducted a complete water analysis and gas analysis to get the most up-to-date data on the field, which show us we had both an increase on the CO2 content, as well as increase on the acetic acid content, which directly impacted the corrosion rate that we were expecting. And then we did a corrosion model update to assess what that will be, and a flow regime to assess what the water wet areas were in comparison to the previous history of that asset. So comparing both the flow patterns in the corrosion model, we were able to identify what areas of high risk were there in the system. During the early life, the water wetting risk was low to moderate. Towards the midlife, we start seeing a higher probability of water wetting risk at the section of pipeline upstream of the second well. And then towards the late life, that section expanded. It was still near the same at the same location, but it became a significant portion of concern. Mainly due to the bathymetry, that area had a higher water holdup and water wetting risk, therefore. So overall, the results of this assessment improved the risk visibility. We identified what areas on the pipeline require further assessment, and we prioritize and progressively advance assessments of activities. The forward IM plan includes NDE of the high water wetting areas to screen for general corrosion as well as localized effects, reestablish CI injection, and then continue those periodic monitoring activities such as coupon monitoring and fluid sampling. So in conclusion, knowledge is well documented through the risk assessment process. It helps us link key integrity data to the degradation mechanism and how that changes over time and throughout the life of the asset. Data gaps will lead to a more conservative risk evaluation and therefore warrant more assessment. A good example of this is when we have fabrication records available. It helps us utilize actual measure wall thicknesses as opposed to nominal, which might be a benefit when looking at fitness for service of a component versus when we don't have corrosion allowances or they're not well known. That will lead to a more conservative approach to risk. Starting in the project phase, feedback from the operational experience, integrity experience from both SMEs as well as the operator can help improve design and also minimize data gaps from handover during projects to operations. A key example of this, we were working with an operator where several components had, several jumpers had hot spots that we were observing very rapid corrosion. And so in subsequent tiebacks, the feedback was implemented in selected cladding at those locations and therefore more effectively mitigating the risk for those assets. Documenting monitoring requirements and identifying accurate KPIs in your IM plan, as well as identifying alternatives to monitoring when applicable for inspection techniques. As I mentioned before, the cost and risk associated with inline inspection are typically a deterrent for implementation, but there are things that we can do and evaluate to build up to that, such as doing NDE of several tiebacks to identify if any is required for inline inspection and then prioritize that field as opposed to doing ILI on every single tieback to a facility. And finally, life extension. As we mentioned before, as we're documenting this history of the asset and how the integrity data affects the degradation mechanism, we are already building our case for life extension. We have a good foundation, and then it's more effective in optimizing the IM plan and what are the recommending activities for life extension. A great example of this is utilizing data from retrieved components. We had several jumpers that had been retrieved in a field, and that helped us identify what locations to prioritize for NDE as opposed to just going out there and doing every single component. We were able to optimize that plan. And that is the conclusion of my presentation. I'm looking forward to answering any questions that you might have. Thank you so much.
Thank you, Johanna. Yeah, let's get started asking some questions. Okay, let me see. First one, was ILI considered for the flowline case study?
We did look at ILI. The field had not been done operational pigging, so there was no cleaning that was done of the pipeline. So the risk associated with conducting ILI was considered too high. And in addition to that, it was we will have to do a bidirectional pig at that time because the flow loop was not available, which also increased the risk and cost. So the goal of our assessment was to identify if ILI was really a requirement, and we identified risk areas to do NDE and to evaluate and screen for corrosion before even recommending ILI. But we did evaluate it.
Okay, thank you. Next one, should I consider NDE of retrieve components?
Absolutely. I think there's a lot of value of getting data on components that have been retrieved. Typically, for some subsea components, we just do visual inspection, but for rigid jumpers especially, we have done NDE, and that has helped us identify what are the corrosion hotspots for a particular jumper configuration and field conditions.
Okay, thank you. Let me see. Next one, what is the approach for defining KPI limits for corrosion rate?
We look at both allowances that were considered in design, as well as what is the service life, what the corrosion models tell us about the CI inhibition efficiency, and that's how we arrive to the limits of acceptable corrosion rate.
Okay, and I have one more, so if anyone else has any more questions, feel free to type them in the box. But for now we have, how often should integrity data be reviewed?
It depends on the risk. We typically recommend annual risk assessment updates, but sometimes with a component that has a higher risk, we might look at integrity data on a quarterly basis or a semi-annual basis. It also depends how often data is being retrieved, which sometimes is not entirely to the operator if it's has a tie back to another facility. So we have to work together in both leveraging the risk assessment as well as what is actually actionable for operations to conduct.
Okay, great. Well, that is all the questions we had. So I just want to say thank you so much, Johanna, for all the information on the topic. That's all the time that we have for today. But as we mentioned earlier, if you think of another question or you'd like to continue this discussion, you can contact Johanna directly using the details provided here. Thank you to our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series happening at the end of each month. You can check out the 2H website and LinkedIn for more details and to sign up. And again, please look out for the recording of this webinar in your email in the next 24 hours, and we hope you all enjoy the rest of your day. And thank you.